In the last class, we had finished discussing the sampling paradigm under the subspace model, where we talked about abstract subspaces and how we can do sampling under those abstract subspace models. In particular, we had talked about the case of sampling under the model of shift invariant subspaces. And the basic message we got was that if you are, let's say that you have a subspace S, which is a subspace of a Hilbert space, an inner product space, and it is a shift invariant subspace, which means that if we shift any function within that subspace or any element of that subspace by some multiple of your time period, you get back another element within the same subspace. And of course, the examples of this are you either have class of band-limited signals, or you have class of piecewise constant signals, or you have class of splines, which is part of a question in your assignment. If that is the case, then we know that there is a single function that multiple shifts of that function are going to generate basis of that subspace. So if we have S being a shift invariant subspace, and then we have something, a function which I am going to call phi t of t, all shifts of that generate basis of this subspace. And for this class we talked about earlier, we are going to assume that we are only working with orthonormal basis. Is an orthonormal basis of S, then the general sampling paradigm goes as follows. So given some x of t, which belongs to the vector space, which for all intensive purposes so far we have considered L2R, the space of finite energy signals. Given xt, in this we basically first write down the approximation of this function in the shift invariant subspace given by the formula that we have seen, the projection formula, that is simply given by inner products of that function with all the basis elements, phi t of t minus nt, and multiplied with the same basis element afterward, n equals minus infinity to infinity. And we said that these inner products correspond to the samples, and this whole expression that is given by x tilde summation of these samples times the phi t's, this corresponds to the interpolation. The hardware implementation of that is simply given by, we saw that the inner product can be expressed as first a filtering operation followed by sampling. So these samples can be simply obtained by, you have x of t coming in, you filter them by a pre-filter which is given by the time reversed version of your generator function, which gives rise to the basis. And at the output, you simply take samples every capital T seconds. So this is how you get your samples. Okay. The only thing that changes as you change your subspace is simply what is this pre-filtering. In the band-limited case, this is given by the sink. So if you have band-limited signals, then phi t of t is simply given by sinc of t over capital T. Similarly, if it's a constant, piecewise constant class, then we saw that this is simply given by, and if you want to orthonormalize them, you should divide them by square root of t. This is given by 0 to t indicator function, and of course divided by square root of t. And in terms of reconstruction, we simply said that you take your samples. So we are going to call these samples x tilde n. So let's call them x tilde n. You take your samples, you convert them into impulse train, which means that you get x tilde of s, which is just the superposition of these samples times the impulse train. And then you have a post filter, which is simply this feed generator function again, and at the output you get x tilde of t. So once again, this phi t of t in the band limited case will be simply a sinc. For piecewise constant, it will be this indicator function. And the basic sampling theorem will be that this x tilde of t will be equal to x of t if and only if this x of t belongs to the subspace. For example, if you were sampling a band limited signal, then you will get back that same signal. If you are sampling a signal which was not band limited, then you will get back an approximation to that band limited signal. Similarly, if you are sampling a piecewise constant signal, then doing this will give you exactly the piecewise constant signal that you started with. If you are not doing that, then what you will get is an approximation to the signal you started with in the piecewise constant class. That is precisely one of the questions in your assignment. That is precisely what you will be doing, approximating 3 different signals under different models. Now the question of which signal class to use, we talked about it earlier too, and you will again see it in your assignment. That depends upon the signals that you are dealing with. One of the properties of band limited signals is that they are rather smooth in time. They don't change abruptly, otherwise they won't be band limited. So if you have functions which can be approximated by band limited signals, they don't have sudden jumps, they don't have discontinuities, jump discontinuities, then sampling under the band limited model is a good idea. But if you have signals which have sudden jumps, jump discontinuities, then perhaps piecewise constant model is a better model. And again, you are asked in your assignment, given the 3 signals, to play with them and really figure out which model is better for which class of signals. Okay. There are things which are intermediate to that. They don't have that strong jumps or discontinuities, but they are not as smooth as band limited signals, and that's where the class of spline functions come in. We are not going to study that formally, but in the assignment I have the definition of that spline class given. So depending upon the class of signals you are working with, you will use different kinds of subspaces. That's about all that we are going to cover as far as continuous time sampling right now goes. We'll come back to it when we have to talk about multi-dimensional settings. So what we are going to do in the next couple of lectures is now shift our focus from continuous domain to the discrete world. We are now going to talk about sampling of discrete sequences. In this sampling of discrete sequences, we are going to again reuse the formula that we derived. We are going to again think about signals or sequences given as subspaces, and we'll simply reuse the projection expression that we have derived earlier and get back to notions of downsampling and upsampling in the discrete world. So we are now going to take a break from the continuous world and we are going to the discrete world. In particular, we are going to talk about, just like in the continuous world, we talked about the class of finite energy signals. In the discrete world, we are going to focus on signals or the class which is called L2Z, sequences which have finite energy. Okay? That will be our focus. Sequences of finite energy. So this L2Z is defined as all sequences such that when we take the square of the absolute values and we sum them up, the total sum is less than infinity. Just the discrete analog of the integration expression for finite energy that we saw earlier. Now, our goal in here is that we are given sequences which are already discrete. These are discrete sequences, and we want to talk about sampling of these sequences. We want to sample them, and the traditional term that is used is downsample, but we are going to not overemphasize the word down. We are just going to sample them. We are given xn, we want to downsample it to get, I'll denote that xdn. And of course, if once we sample something, our ultimate goal is we should be able to reconstruct that thing. So we want to go back to x of n if possible, or its approximation using these samples xdn. Okay. So very similar objective that we talked about in the case of continuous world. We just have to make sure we understand some of the terms. What does the inner product, for example, mean in the world of L2Z? So L2Z, we won't go into that, but it is a normed vector space. It's a Hilbert space. It has all the nice properties. And inner product on this is defined as if you are given two sequences, x and y. The inner product is simply defined as xn and y conjugate and n equals minus infinity to infinity. You can verify that it indeed satisfies all the properties of the inner product. But we also have to define other analogs of the operations that we have done in continuous time. So in continuous time, we had the notion of sampling, which was better defined. We said we get a continuous time signal and we take its samples every t seconds. Well, in the discrete world, the notion of sampling can be defined, or at least point-wise sampling can be defined in a similar fashion. You are given xn, and you want to collect its samples every, let's say, m. Now, we don't have units, so we can't say seconds, right? Every m samples of the original sequence. Okay? So what we want is that we are given xn, and the notation we will use is this standard notation, which is also called decimation or downsampling, xdn, which simply means that you collect all the samples every m these unit steps of discrete time. Okay. xdn is simply x and m. And of course, the constraint is that m has to be an integer, a positive integer. So unlike in the continuous world where t could be any number, in the discrete world, m has to be a positive integer. The operation of doing that in hardware, of course, is very simple. You are given a sequence and you just drop every m-1 sequence values. So if your xn is given by this kind of a sequence, and let's say this is your 0, 2, -2, and you're talking about m equals 2, then your sequence basically just drops this value, and this value, every m-1 values in between, and you get xdn. So after I pass this xn by this factor of 2 downsampling or decimation, I get back xdn, which is simply 0. So this comes here, this comes here, this comes here. At -1, its value will be this. So exactly the same expression, you just don't have the notion of continuous time. Just to give you all the names, in some text, especially the classical text, you will see the word written decimation for this or downsampling for this by a factor of m. The other thing we do in the continuous world is this expression, if you remember, of taking the sequence. So we used to take a sequence, x tilde n, and we will convert it into an impulse train. And we used to get back this xs of t, and of course in impulse train we had this time period t, the sampling time going in. We used to get xn delta of t minus nt. There is a similar analog of that we will be seeing in the discrete world, and that analog works like this. You are given some samples x tilde n, and you convert them into an impulse train, but the impulse train is discrete now. So you have this conversion into an impulse train where the time period now is capital M. Again, it has to be an integer because you are dealing in the discrete world. And the output will be calling that x tilde e of n, which looks like simply x tilde of n delta of n minus km. Now, in the classical literature, there is again a shorthand for that, because creating this inside a digital machine is very simple. So the shorthand for that is given by just the reverse of what you have for downsampling. You put an up arrow and the number m. So you have x tilde of n, and you have x tilde of e of n. Okay. In the classical literature, this expression, this operation is called an expander or expansion. What does an expander though do? You are given a sequence. You're given x tilde of n, and this is your sequence value. The expander effectively puts in m minus 1 zeros between two successive samples. You can work out the expression for this impulse train, but effectively what it does is it takes each sample, and after that sample it puts m minus 1 zeros and then puts the next sample after that. So if I have m equal to 2, what will happen is my new sequence, this is my x tilde of n, my expanded sequence. So let's say if this is my 0 will be here. But this next sample, which was at index 1, instead of that, I will put a 0. And this next sample will go after that. So this will come here. And then I will put a 0 again, and the next sample will go after that. Then I'll put a 0 again, and the next sample will go after that. And similarly, there will be a 0, and then this thing, next sample will come in. 0, and this will go. So while decimation or downsampling basically takes a sequence and throws away every m minus 1 samples, the expander takes a sequence and puts m minus 1 zeros in between two samples. Mathematically, they are complete analog of you have that switch closing every t seconds in continuous time. You effectively have a discrete switch closing every m minus 1 samples. You keep every mth sample, throw away the next m minus 1 samples. Keep the next sample, throw away the m minus 1 sample. That's decimation. In expansion, you have complete analog of that convert to impulse train, which is effectively you take a sample, put m minus 1 zeros, take another sample, put m minus 1 zeros. Okay? So we'll be using those two blocks of an arrow down or an arrow up showing decimation or expansion as simply replacements of what we did in the continuous time world. Okay. Now there is a third analog that we need to look at, which was that we talked about in L2R. If you think about the inner product can simply be written as a filtering operation followed by sampling. That's how an inner product is implemented in the continuous world. Now let's see if we can show or argue that the same will happen in the discrete world of L2Z. So what we want to argue, and from here on I'm going to assume that all my sequences are real valued. So my sequences are real valued. and I'm given two sequences given xn and yn. I know that I defined the Cn to be xn convolved with y of minus n. Okay. What I want to argue is the following. The inner product between the two sequences, just like the inner product in the continuous world, we argued that that is given by simply the convolution of one function with the other function time reversed and then sampling. We want to argue the same thing. We want to argue that the inner product between x and y is simply the convolution of xn with the time reversed version of yn and then sampled at n equal to 0. Okay. So let's see if that is indeed the case. So let's look at the convolution expression. We have xn. So well, the indices go from minus infinity to infinity. xm y of minus n minus m. That is simply equal to mx of m y of m minus n. Okay. And now if I sample this at n equal to 0, I get xm y of m, which is indeed the inner product between x and y. Now let's look at the other case. Let's say that I have x and I want to take the inner product with y shifted by some multiple of m. So let's say I want to take inner product of x with y shifted by km, where I'm defining yn minus km as y of n minus km. Okay. Just a function shifted by some amount. I'm going to argue that that is actually equal to this convolution with shifted with time reverse version of y sampled at n equal to km. So let's look at Cn again. I have Cn again, just look at from above, xm y of minus n minus m. And I'm going to now just change the order. It's m xm y of m minus n. And indeed now if I replace n by km, I get back m xm y of m minus km, which is equal to x, inner product of x and y of n minus km. Okay. The point is that every inner product between one function which is fixed and the other function which is a time shifted version of the original function can be simply computed by filtering that function with the time reverse version and sampling it at some time. So if I want to compute, let's say I want to compute this, x and y of n minus km for k minus infinity to infinity. The way to do that will be simply I get my sequence xn, then I filter that with y of minus n, and after that I sample it at multiples of km. And sampling, we use this notation M. So the output of this operation, filtering and then this decimation, downsampling, sampling, whatever term you want to use, that is equivalent to computing inner products of X with all possible shifts of Y and, okay, which is very similar to what we did in the continuous time case, where we had to compute inner products of your function with, let's say, a sinc, shifted versions of sinc. We said to compute inner products with shifted versions of sinc, all you have to do is filter it with the time reverse version of sinc and then sample it. So it's exactly the same analog. Okay. In the continuous world, what we did was we had x of t, and we were trying to take samples of sinc of t minus nt over t, square root of t for normalization, and we said that is equivalent to x of t, simply filter by sinc of minus t over t, minus doesn't matter because it's symmetric, and then take samples every t seconds. There is a complete parallel between the two words. If you want to compute all possible inner products, all you have to do is filter and then take samples. Okay. So what we are going to do is, with these equivalents, we are going to now talk about, if you are given a subspace model in L2Z, if you are given sequences which belong to a subspace model, how do you sample them in the discrete world and how do you reconstruct them? And the solution will be very similar to the continuous time expressions that we saw. Okay, so let's start with now, once we have developed these equivalents, let's start with sampling of discrete sequences. We talked about it earlier about sampling theory. The first rule of sampling is that you have to have a mathematical model for the class of signals in which you believe your signal lies. And now that we have derived this abstract notion of subspace models, we are going to start with that. So our signal model is that the sequence we want to sample, xn belongs to a, and I am going to now focus on only the case of shift invariant subspaces, but it can be extended to non-shift invariant subspaces too, belongs to a subspace of L2 of Z. Let's call that subspace, we have S, which is this subset of L2 of Z. Now we are going to put on the hat of this vector space and subspace model. So if we are given a subspace of a vector space, again, keep that in mind. It doesn't matter now. Once we start talking about subspaces and vector spaces, it doesn't matter what does a vector in that space really mean. It could mean a continuous signal or it could mean a discrete sequence. From the perspective of mathematics, we don't care. The general principles remain the same. So now you are just talking about, you have signals that come from a subspace. What is it that we have learned earlier? If we talk about subspace, then we should try to find an orthonormal basis for that subspace. So then we find an orthonormal basis for this S. And because it is shift invariant, we only have to think about one function. All possible shifts of that will give you back that, will give you the basis for that subspace. So without loss of generality, I'm going to call it phi of M. And you have all possible shifts of that subspace. Okay. Of course, if you are dealing with a vector space of sequences, your subspace basis will be sequences. Once we have the basis found for the subspace, what is it that we have to do next to find the approximation of that, to find approximation of a sequence in L2Z within that subspace? We just use our projection formula that we have been using for the last 2 or 3 lectures. So if I want to find an approximation of Xn, because I don't know for sure whether Xn really lives in that subspace or not, well, that is simply given by X tilde of n. What do? We first take inner products of our original function, original sequence, with all the bases of my subspace. So the basis of my subspace are this phi m. I'll just write the indices just to make clear that we have the shifted versions of them. And then we multiply with the same basis element. And we sum all of these up. So this is the approximation based upon the projection formula that we derived earlier. And just going back by the same thing that we have been doing, these inner products, we will call them samples. So these are our samples of the discrete sequence. So these samples, I'm going to denote them by X tilde d of n. Okay. And now we can ask the question, how is it that we are going to implement this sampling operation? And we already talked about it. The sampling operation simply corresponds to I taking inner products of my sequence with all possible shifts of this phi m. So the general sampling architecture is going to be exactly the same as in the continuous time world. We just compute convolution of our sequences with these phi m's, the time reverse versions of them, and then we sample them every m samples. Okay. So if you want to think about what is the exact sampling operation that you can carry out, it will look like you want to compute all these inner products, which means that in goes xn, and you have a filter which is simply phi m of minus n, time reversed version of it. Okay. At the output, you sample it every m samples, so you have a decimation by a factor of m. And what you get back is X tilde d of n. Again, this thing, we call this pre-filter. And it is exactly the same as in your continuous time, where the pre-filter was given by the time reverse version of your generator function. Now you have a generator sequence. Instead of that sampling every t seconds, you have sampling every m samples. The next question becomes, how do you reconstruct this sequence x tilde n from x dn? And that is, of course, given right here. These are your samples. You simply multiply them with phi m n minus km and you take the summation. So let's see how we can write that further. If you want to get back x tilde m, we can write this as summation k equals minus infinity to infinity. That is x tilde d of n phi of m n minus km. Okay. Now this phi of m n minus km, I can use the convolution property. I can say the delta of n minus km convolved with phi of m n is equal to phi of m n minus km. Just the same as in the discrete, in the continuous world, if you convolve a function or a sequence with an impulse, the only thing that happens is that function gets shifted to the location of the impulse. So I can replace this with this expression, and what I get back is k minus infinity to infinity x tilde dn delta of n minus km convolution with phi m of n. And now since convolution is a linear operation, I can take this whole thing outside the summation. X tilde dn delta of n minus km, and I just convolve that with phi m of n. If you look at this and you try to remember what we talked about earlier, what is this operation doing? This operation is the expansion operation that we talked about earlier. It's taking samples of x tilde dn and it's putting them one sample m minus 1 zeros, another sample again m minus 1 zeros. This operation is nothing but the expander operation where you simply put m minus 1 zeros between m samples. So this is expansion of x dn to x den. So the reconstruction essentially is saying you take your samples and then you do an expansion by a factor of m, and finally what do? You convolve it with phi m of n. So this is the convolution operation then that you can carry out by filtering. So if I collect both of these facts together, we can say that reconstruction in the discrete world, reconstruction of x tilde of n from its samples x tilde d of n, that is given by you first do an expansion by a factor of m, and then you do filtering with phi m of n. And what you get back is x, this is x tilde d, what you get back is x tilde n. Okay? And of course, just like in the continuous time world, this thing is called post-filtering. So effectively, as long as you have a subspace model for your discrete sequences, the way to sample, or you can call them subsample or downsample, discrete sequences is exactly the same as in the continuous world. You only have to make sure you just replace some operations with their right counterparts in the discrete world. You get a sequence, you first filter it, then you do downsampling or decimation. You want to reconstruct the original sequence from the downsampled sequence. You take that sequence, you upsample it, and then you filter it again. And the sampling theorem will be that as long as your original signal belonged to the subspace that you started with, you doing this kind of sampling you will not lose any information. Otherwise, you will get only the best approximation to that. So in the discrete world, we are doing things a little in the reverse order. In the continuous world, we started with the band-limited signal model and derived the Shannon-Nyquist sampling theorem the way you probably have seen in the undergraduate. And then we said, well, it is nothing but thinking of taking your signal and projecting it onto the subspace of band-limited signals. But since we are now sort of expert on doing this subspace-based sampling, in the discrete world, we are now taking a different approach. We are saying, let's start and ask what is the abstract version of sampling in the discrete world. And we have derived that. And now we can take that and specialize it to any signal model that you want to work with. So as long as we understand this, someone comes to you and says your sampling model your subspace model is X, Y, or Z in the discrete world, you simply replace these filters because everything else is fixed. The downsampling and the upsampling, those are just operations. The only thing that changes is what goes into your pre-filter and what goes into your post-filter. And that is determined by your subspace. So if I give you a subspace, you simply replace it in the right fashion and you get back your sampling theorem for that subspace signal model. So far we have seen an abstract model of sampling of sequences. Let's now make it more concrete by talking about a very specific signal model. Right now we only said assume it's a subspace. So now we are going to talk about specific signal model. So we have a special case now of sampling of band-limited sequences. Sampling of band-limited sequences. And we are going to see what does CM in that case look like, or what does sampling and reconstruction or downsampling, upsampling, these expressions look like in that case. So let's first make sure we concretely understand the notion of band-limited sequences, not now continuous time signals. And the notion is exactly the same as in the continuous time world, with the only caveat that the discrete time Fourier transform is periodic. So we have to be a little more careful about that. But the definition exactly goes the same way as in continuous time. If xn is a member of L2Z, then we know that it has a discrete time Fourier transform, which we will be calling xe to the j omega, which is simply given by n minus infinity to infinity x of n e to the minus j omega n, where this omega is in radians. And of course, I'm confident that you guys all remember the discrete time Fourier transform is periodic with a period of 2 pi. And for most of our discussion, we'll be working with the principal period of minus pi to pi. Omega will be belonging to minus pi to pi. And given the discrete time Fourier transform, there is also the inverse formula, which is 1 over 2 pi. We simply integrate from minus pi to pi x of e to the j omega, e to the j omega n d omega. So the discrete time Fourier transform of sequences itself is continuous, and it is periodic with period 2 pi. So what is the definition of band-limited sequences? I'll use the same term, omega n L2z. This is defined as all sequences in L2z for which the Fourier transform becomes 0 after omega n until pi. We can't just say it becomes 0 for all omega n for all omega greater than omega n because it's periodic. For all omega belonging to omega n to pi. So if I have xe to the j omega, two pi minus 2 pi 0. So this is minus pi to pi. This is of course a band limited signal or sequence. On the other hand, a sequence which never becomes 0, whose discrete time Fourier transform never becomes 0 between minus pi and pi, that's not a band limited sequence. Okay. So exactly the same definition as in continuous time world. And given sequences, now you can ask yourself, well, how do I even reduce the amount of samples that I have in that sequence? Downsampling or just sampling. And under what conditions I can recover it back. Now instead of doing the usual thing that we did with continuous time, we are going to use just the formulas that we derived earlier. Okay. So for us to be able to use those formulas, we have to have a couple of things. Number one is we need to verify that this space of band limited signals is a subspace. Okay. Which means you at a informal level, you add two signals and you get back, you add two signals which are band limited, you get back a signal which is band limited. And that is trivial to verify. You can't add two band limited signals and get a signal which is not band limited. So the first thing we have is that BL omega n L2Z is a subspace of L2Z. Okay. Once we have that, the other thing that we need is an orthonormal basis for this subspace. Now again, I'm not going to try proving that, but it turns out that the discrete sink n minus km, which is defined by sink of n minus km over m divided by square root of m for k all integers. This is an orthonormal basis of the space of band-limited signals which are band-limited to pi over m. So we have found that the signal model we are dealing with, the sequences which are band-limited, it's a subspace, number one. Number two, that subspace has orthonormal basis. When we are talking about the bandwidth being pi over m, the subspace has orthonormal basis sinc n minus km over m divided by square root of m to make things normalized. After that, the solution should be easier. What are the samples? So if we want to sample signals or sequences under the subspace model, the samples are simply given by inner products. Inner products of, let's say you are given xn, you simply take inner products of that with n minus km, okay, for k minus infinity to infinity. Those are your samples. Okay. And we know, we have talked about it now many times, if you want to implement this in hardware, what it is given by is you take your xn and you filter it by g of minus n, where g of n is simply, so if I define g of n is equal to sinc of n over m divided by square root of m. You simply filter it with the time reverse version. Now in this case, actually the minus n doesn't matter because it's symmetric around 0. Okay, so I could have just written filter it with g of n. And then after that, you simply sample at a rate of every m samples. Okay, these are your samples which I will call x tilde d of n. Now let's look at what this filter looks like though. So this g of n is sinc of n over m over square root of m. What is the Fourier transform of this filter? So what is g of e to the j omega? What is this filter doing? The Fourier transform of this sinc is simply this square function minus pi m to pi m with the height of square root of m, and of course this will be repeated every 2 pi. This is minus pi, this is pi. So what this is saying is, in the case of band-limited sequences, what is the first operation that you do? You low-pass filter. What did we see in the case of continuous time signals? If we are going to sample band-limited signals, we first low-pass filter to the bandwidth. It's exactly coming out to be the same expression. If you want to sample sequences which are band-limited, you low-pass filter them to the bandwidth you think they have, pi over m. And then after that, you do downsampling by a factor of m. Okay. Now let's look at reconstruction. You can call it reconstruction or interpolation. I'll just also put interpolation here. Now interpolation said that we will get x tilde in. That should be simply equal to the sum of all the inner products, which are just x tilde dn. So x tilde dn x tilde dn multiplied by g of n minus km. K equals minus infinity to infinity. Sorry, x of k. So if you want to talk about interpolation, that is simply given by the sum of all the inner products multiplied by your generator function or your basis elements. So in this case, we have the sequences, which is x tilde d. We multiply them with xn minus km. And as we talked about it earlier, I can simply write that as x tilde of dk times delta of n minus km and convolved with g of n. We have already derived that in the general case. So, and this is simply the upsampling operation by a factor of m. So the reconstruction or interpolation says that you take your x tilde d of n, you do an upsampling by a factor of m, and then you simply do filtering with g of n, and you will get back x tilde in. Now what is this gn again? It's exactly the same low-pass filter. So what do we do in the continuous time world when we are reconstructing from samples? We take our samples, we convert it into an impulse train, and then we low-pass filter it. We low-pass filter it to the cutoff frequencies that we think our signal has. It's exactly coming out to be the same thing in the discrete world. We take our sequence, we convert it into a train of impulses, which is just this upsampling operation, and then we low-pass filter it at a cutoff of pi over m. And what do we know about our general subspace principle? That if you approximate a signal that lives in the subspace, then you get back that same signal. The effective meaning of that in the case of band-limited sequences is that if x of n is band-limited to pi over m, so if you have a sequence which is band-limited to pi over m, and you subsample it, you throw away many samples, you can still reconstruct that signal from those samples by first doing this upsampling or expansion followed by filtering. If xn is band limited to pi over m, then we are guaranteed that x tilde in equals to x of n. That follows from the fact that if xn is band limited, then Xn belongs to the subspace. And if a signal belongs to the subspace and you do this projection, you get back the same signal. And you are given this as a problem in your assignment to show. If you take a signal from a subspace and you project it onto that subspace, you get back the same signal. So if Xn belongs to the space of band-limited signals, band-limited to pi over m, then we are guaranteed that xi tilde n equals to x of n. So in the case of band-limited signals, we can easily address what should m be. Our m has to be such that our signal is band-limited to pi over m. If m is large, it has to be even constrained to a smaller region of bandwidth. If m is 10, your signal must be band-limited to pi by 10. Stated differently, if your signal is band-limited to pi by 2, you can't have m bigger than 2. Okay? And we'll look at it in more detail when we focus only on the frequency domain aspects of this decimation and the upsampling and expansion. But the key thing to take away from this is that because we were armed with the formula for projection onto a subspace, the general trick of you are given a subspace, you know its orthonormal basis, you can write down what the samples will look like, you can write down what the construction will look like. We did not have to redo those picture-based sampling theorem as we did in the case of continuous time signals. We simply followed that same trick forward, and it ends up that the structure looks very similar to sampling of band-limited signals. Okay? But since we have this architecture, we can apply it to other signal classes beyond band-limited signals.